Today we're diving into the fascinating world of opioids and how they interact with our brain's intricate reward system. First off, let's talk about opioid use disorder, the medical term for when someone develops a problematic dependence on opioids like heroin, prescription painkillers, or synthetic options. It's a serious issue, but understanding how these drugs work can help us see why they can be so addictive. At the heart of this story are the opioid receptors. Think of them as tiny lock and key systems scattered throughout the brain. There are three main types: the mu opioid receptor, or MORE, the K opioid receptor, core, and the delta opioid receptor, DOR. Our bodies produce natural opioids, endorphins, enkephalins, and dynorphins that bind to these receptors to regulate pain, mood, and stress. When opioids like methadone or buprenorphine enter the scene, they mimic these natural messengers by binding to the same receptors. Methadone is a full agonist at the mu opioid receptor, effectively turning it on, while buprenorphine is a partial agonist, giving a more controlled activation. These drugs work through sometimes called the G protein-coupled receptor, or GPCRs. Imagine them as switches that, when activated, trigger inside the cell, signaling cascades. Once an opioid binds to the receptor, it activates a pathway involving GIL proteins. This leads to the inhibition of adenylyl cyclase, an enzyme that produces CAM, a molecule involved in many cellular processes. Less CAM means decreased neuronal excitability, which translates into pain relief and feeling of euphoria. But it's not just about switches. The receptor also recruits beta-arrestins, which can cause receptor internalization. Think of it as cell pulling the receptor inside to prevent overactivation. This process can lead to receptor desensitization over time, meaning the brain becomes less responsive to the drug, contributing to tolerance. Biased agonism comes into play, a fancy term for drugs that preferentially activate certain signaling pathways over others. Some opioids might favor G protein pathways, which provide pain relief with fewer side effects, while others might trigger beta-arrestin pathways associated with adverse effects like respiratory depression. When opioids activate mu opioid receptors on GABAergic neurons in the ventral tegmental area, they inhibit these neurons, which normally suppress dopamine neurons. This creates a vicious cycle. The brain's reward system is hijacked and natural rewards lose their appeal. In summary, opioids interact with specific receptors in the brain, triggering a cascade of signals that lead to pain relief and euphoria. But repeated activation can cause tolerance, receptor desensitization, and profound changes in the reward circuitry. Thanks for joining me on the brief tour of the brain's opioid and reward system.